So today we're going to look at some other tools for computing limits of sequences. And so we'll start with a bunch of rules, and these might look a little abstract, but we'll find some examples where you'll see exactly what's going on, and they're not that bad, I promise. But the overall intuition for all of these rules is that you can break up a single limit into multiple parts as long as each individual part exists. And so, for example, if we're talking about the sum of two sequences and you want to take the limit, then that's the same as just taking the limit of each sequence individually and then adding it together. The same is true for differences. The next rule just tells you that the same thing is true for products. And so, in other words, the limit of a product is the product of the limits. The same rule is true for division, which is what this third bullet point tells you right there. And the last rule just tells you that whenever you're taking a limit of a constant times a sequence, you can just pull the constant out front, and that makes no difference. All right, so let's quickly look at two examples. Well, one is an example and one is a non-example of how these rules work. So for this first problem right here, when we're taking the limit of 13 times some garbage, first of all, we can see that 13 is a constant in terms of n for this limit. And so by the very last bullet point here, we can rewrite this as 13 times the limit as n goes to infinity of the stuff that's inside. And at this point, of course, you already know sort of that the leading terms here are what's going to dominate, and so you can probably tell that that limit is going to be 1, but I just want to get some practice using these limit rules, and so I'm going to rewrite it just so that we can see what the rules would tell you. And so another thing that you could do is break up this fraction into two parts. One is just 1, and the other one is 12 over n squared. And so here I'm just breaking up this numerator into an n squared over n squared plus a 12 over n squared and simplifying the first term so that it's 1. Then we could use the limit rules that we just talked about to rewrite this as the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 12 over n squared. Intuitively, that's what you already would have done if you were computing this limit to begin with, but here I'm just writing out the sort of formal reasoning for this. This limit right here is just going to be 0 because the 12 over n squared, the denominator goes to infinity and the numerator is just a constant. The other one is just 1 because it doesn't change with respect to n, and so overall we just get 13 times 1, or in other words 13, which is probably what you could have guessed from the beginning. But again, the point of this was just to see how these limit rules work. Now, let me show you a bad way of breaking up these limits. And so we could write the limit as n goes to infinity of n squared over n squared plus 1. We could attempt to break this up into two limits by writing the limit as n goes to infinity of n squared over the limit as n goes to infinity of n squared plus 1. But we're going to see really quickly that this is not true. And the reason for this is because if we were to evaluate each one of these limits now, the top one would evaluate to infinity, the bottom one would evaluate to infinity, and that's an issue because neither one of these limits existed then. And so we're not allowed to apply those limit rules because these limits don't exist. And so another reason why we can see that this is going to be a problem overall is that we're used to seeing this sort of thing with L'Hopital's rule. This is an indeterminate form, and so we don't really know what this means.